Hello everyone, welcome to Chemistry Lovers. So this is my second video of tautomerism, and in this video I have shown you the keto-phenol tautomerism and the ring chain tautomerism, and this is about my last video of tautomerism. So you can see here I have written the keto-phenol tautomerism, where I have written this phenol compound and it converted into its corresponding keto form, but we know that the enol configuration is very much stable, especially for phenol, comparatively than its keto, and its main reason is the bond energy, because phenol when exists in enol configuration, then it is very stable in nature and its corresponding bond energy is about 36 kilocalorie per mole, while if we shift it into its corresponding keto configuration, then only its bond energy is about 20 kilocalorie per mole. So with respect to bond energy, its enol configuration is very much stable in nature, its corresponding keto form. I have told you in the previous video that keto configuration is generally much more stable than enol with respect to bond energy, but here the reverse situation take place, especially for phenol, and some molecules take place like Acac, enol, phenol, and so these molecules show reverse situation, that is, this molecule mostly prefer to exist in enol configuration comparatively than its corresponding keto form. Now in this case the bond energy is the main reason, so that's why phenol exists in enol configuration, not in keto configuration. Though keto configuration also show extended conjugation, here you can see the benzene ring is converted into this corresponding form, but you should also observe that the aromaticity of the system is destroyed in this case. So if a system, the aromaticity is destroyed here, so its stability also reduced with respect to the former structure. So that's why the phenol is mostly exists in this case in this structure, enol form, not in this structure. Here I have written, you can see that the phenol exists in 100% enol configuration and there are no keto form exist. Like some molecule mostly prefer to exist in keto configuration because keto is usually higher in stability comparatively than enol form, as 15 kilocalorie per mole bond energy present in this case. But like phenol or acetyl acetonate, so there are some molecules also present in universe which show the reverse situation. Okay, here I have also drawn another molecule. You can see the molecule, and its name is dimethylene acetaldehyde. Dimethylene acetaldehyde. Here the molecule, you can see 3 methyl group present with respect to meta position with each other at the phenyl ring, and this alpha hydrogen is transferred here and the double bond here take place, and this is the OH group. So this is dimethylene acetaldehyde. This molecule also prefer to stay in keto content, not in enol content. Sorry, this molecule also prefer to stay in enol content. Very sorry. This molecule mostly prefer to stay in enol content, not in keto form, because here you can see this alpha carbon become sp3 hybridized having bond angle 109.28 degree. Okay, so there are two bulky mesitylene group present with it, and there is a huge steric interaction take place between them, which destabilize the system much more. But if it converted into its enol configuration, then you can see thus alpha position become sp2 hybridized having bond angle 120 degree, which causes the distance higher between these two bulkier groups. These two bulkier groups are moves apart from each other because the distance is increases, causes less steric interaction, less steric crowding. Less steric crowding makes more stability of the configuration. Here in this case the steric interaction becomes very much higher because the distance is very smaller between these two bulky group. The methyl being also a bulky group and is connected along with the 6-membered phenyl ring, so there is a huge steric interaction take place, but in this case the steric interaction reduces very much higher because the distance is increases. You should know the bond angle 120 degree having sp2 hybridized, so there are these two bulkier groups like mesitylene group are moves apart from each other. Lesser steric interaction makes higher stability of the configuration. So in so here this so there is a question arise that how could we know that whether the molecule exists in keto configuration or enol configuration, right? How could we know? So well, there's a rule that you should observe the structure of the molecule very closely. Like in this case there are two bulkier groups present with the alpha position, and so the molecule mostly prefer to stay in enol configuration rather its keto content, because if it exists in enol content then the steric interaction reduces very much. Steric interaction reduces makes higher stability of the configuration, so the molecule in order to gain much more stability mostly exists in enol configuration rather than its corresponding keto content. Okay, so if you observe the structure closely here, these two bulkier groups are present with the alpha position. So if any molecule containing one or more than one bulkier groups with its alpha position, then you should remember that this molecule or this category molecule mostly prefer to stay in enol content. And if 1,3-dicarbonyl molecule like acetyl acetonato, Acac or ethyl acetoacetate, this molecule like 1,3-dicarbonyl molecule where the middle carbon content if any bulkier group, then this molecule exists in keto content. So in this way we can distinguish or identify that some molecule exists in keto content and another is enol content. So up to this, if you have any doubts regarding this topic, then you can ask me through the comment section. I will definitely sort out your problem. And the ring chain tautomerism is another the rest one. I have bring next video on it later. Okay, so thank you.